Hello, Hire. Today, our new topic is rates and energy profiles. This is another subtopic in Unit 3, which is chemistry and society. This is going to be split into two parts, and lesson one is called Controlling the Rate. This will be a bit of Nat 5 knowledge that we're going to revise on rates of reaction. We're going to learn how to calculate a new thing called relative rate and gain a wee bit of a deeper understanding of the ways that rate can be controlled. So we're going to calculate both average rate and relative rate for some chemical reactions and explain in detail how certain factors affect the rate of reaction. So this is going to include a wee bit more detail built upon the foundation that we already know from Nat 5. So why, first of all, must we control the rate of reactions? So we all know that if a reaction is left to its own devices, sometimes it can get out of control, and this is when explosions and things can happen. But also we want to make sure that the process is economically viable, so that the company, for example, who are making pharmaceuticals are getting enough yield and making enough profit. We also want to make sure that our processes are safe and they can be controlled and collected safely so that no accidents happen. So a wee bit of revision from that 5, we have an open-ended question here. There is space in your booklet to have a wee go at this, so I'd like you to do that, please. A student reacted acidified potassium permanganate solution with oxalic acid. It gives you the formula for oxalic acid there. It also gives you the balanced equation, and it says, using your knowledge of chemistry, comment on how the student could have determined the rate of reaction. So this is purely Nat 5 revision. I want you to have a wee go at that in your jotters or in your notes booklets where there's space, and unpause and I'll go through some things that you might want to include. So first of all, from the equation, we can see that we have a gas produced, which is carbon dioxide. So the first thing you're going to want to say is that you're going to measure the volume of carbon dioxide produced. Now you can do that in two ways, and hopefully you have chosen one of these two ways and drawn a labelled diagram of how you would actually carry out the experiment. Because remember, the rate of the reaction is going to be experiment based if it's average rate. So you're going to want to include your average rate of reaction equation, and you could also put in some numbers, just any numbers you like, to show how you would calculate the average rate. But you're going to want a labelled diagram either of the balance with your conical flask and some loose plug of cotton wool in it to show the mass lost, or the alternative to that is using a gas syringe. So your diagram with your gas syringe collecting your gas. Both methods are absolutely fine to use in this example, but you need to make sure that if you have a labelled diagram, then as always, none of your tubes are blocked. Make sure if you're measuring the volume of gas that your gas syringe has little graduation marks on it so you can see. And obviously, if you're doing the mass lost method, make sure you've got your balance with your measuring cylinder and everything set up on there. So there's lots and lots and lots you could write for this question. You could also, as I said a wee bit earlier, substitute in some random numbers and show how you could calculate the average rate of reaction based on the volume of carbon dioxide produced. So have a go at marking that. Have a wee read through your whole answer and see if you would give yourself 1, 2, or 3 for that question. So we already know how to calculate average rate. This is our new higher learning, which is called relative rate. And it's much, much more straightforward than average rate. So the relative rate of a reaction is the rate at any one particular point in time. So this is not something that you're going to measure using the results of an experiment. But since the rate of reaction is proportional to time, the relative rate can be given by this formula here. So to calculate the relative rate, all you do is do 1 divided by whichever time you're looking at. That will give you the rate at that point in time exactly. So I'll show you the example. So if, for example, the question asked, calculate the relative rate of a reaction at 20 seconds, all you do to calculate relative rate is you do 1 divided by 20, which will give 0.05, and the units are S minus 1. So it's not something you measure, it's not a measurable quantity here. We've not got grams or centimetres cubed or anything like that. The units are only S minus 1 because it's just that one point in time. So that's not the same as average rate. This is much different. Average rate, remember, would be the change in quantity over the 20 seconds. So it's a little bit different. Let's do some example questions. We're going to talk through these and then I'll give you one to try yourself. So using this graph, we've got 3 questions. Number 1 is asking us at which time does the reaction stop? Number 2, what is the average rate of reaction between 0 and 30 seconds? And 3, what is the relative rate of reaction at 150 seconds? So first of all, at which time does the reaction stop then? Remember to be very careful when you're answering these questions, and I would honestly use a ruler. So I would take my ruler and make sure it's flat against the graph, and at the point where the line is completely flat horizontally, that is where the reaction has stopped. You need to be very specific with how you answer these questions, because if the line is still kind of bending as it is all the way up to, I'd say, about here, if you put below 210 seconds, you're not going to get that answer correct. Also, if you put above 210 seconds, then that's the reaction has already stopped for a while. So I would say the straightest part of that graph, kind of horizontally, is 210 seconds. So that's when the reaction stops, because remember, no more mass is being produced or gas is being produced. Number 2 asked us what the rate of reaction, the average rate of reaction would be from 0 to 30 seconds. So this is from Nat 5, hopefully everybody can remember this. The average rate is change in quantity over change in time. So we read off the graph here to say, right, our change in quantity between 0 and 30 seconds is 1.25, halfway between 1 and 1.5. And our time change is 0 to 30, which is just 30 seconds. So if you do 1.25 divided by 30 in your calculator, you should get 0.04, and our units are grams per second. Remember to use whichever unit is on this axis, and then per second for your time. Last question then asked us what is the relative rate at 150 seconds. So we don't really need to use the graph for this question, because remember, relative rate is calculated by doing 1 divided by time. So we have 1 divided by 150, which is 0.006, and remember our units are S minus 1. Okay, so here is a little question for you. The relative rate of a reaction which reached completion in 1 minute and 40 seconds is, and you have 4 options. Now pay attention to the units. You have some with seconds minus 1 and some minutes minus 1, so choose carefully. Have a wee go at this, and then we can talk over the answer in a wee second. So when calculating the relative rate, if you are given a time which has 2 different units in it, it would be beneficial to have just 1 unit. So I personally like to work in seconds because it's a bit easier than minutes. So what I would do is say, right, 1 minute is 60 seconds, 40 seconds added on top of that is a total of 100 seconds. So I would calculate it, relative rate equals 1 divided by time, which is 1 over our 100 seconds, and it's 0.01 seconds minus 1. The problem with keeping this in minutes is that a lot of people will type 1.4 into their calculator, but remember, it's not 1.4. A minute is made up of 60 seconds, so that would be 1.67, which is very confusing. So if it was me, if I were you, I would always keep it in seconds just to make it that wee bit easier. So collision theory, again, something you've been learning for a long time. This is in the second year courses, it's in the third year course, it's in the Nat 5 course. So it's something that you keep building upon all the way up through chemistry. And for a chemical reaction to occur, 2 things need to happen. So this is where we're going to take our depth of knowledge a bit further and look into exactly how this is happening. So the reacting particles, first of all, must have sufficient energy. Now, that's something we're going to look at in more depth in the following lesson. And the reactant particles must have the correct geometry. So they must collide in a specific manner, which is going to help them react. So let's have a look at what this looks like. We have a bromine molecule and a hydrogen molecule here, and they are coming together to react. Now, what happens when they come together is there is something called the activated complex, which is formed. And it's a good idea to know the definition for this off by heart because I have seen it in a few past paper questions. So it's an intermediate stage. So it's a stage kind of in the middle of the reaction. And it is a high energy unstable arrangement. So they can't stay in the activated complex. What they have to do is they either have to form products or they just form reactants again and try again. But that unstable arrangement here is called the activated complex, and it is in this shape. For the reaction to be successful, the geometry matters. So the molecules must be facing the correct way. So if they are facing this way, it's going to be much easier for them to make that square activated complex shape, and there is a higher chance that the collisions are going to be successful. Now, that's not to say that all of the collisions will be successful, but it's going to be a much higher percentage of successful collisions with the correct geometry. If the geometry looks like this, where the molecules are coming side on, it's going to be very difficult and actually impossible for them to form that activated complex. So that means that that collision has been unsuccessful. So it has not produced a product. So like I said, not all of the collisions are successful, even if they have the correct geometry, but these are called successful collisions if they have the correct geometry and have the correct energy or the sufficient energy. The greater number of these successful collisions, obviously the faster the reaction, and that is something everybody should be very aware of from National 5. The more collisions, the faster the reaction. Now, factors affecting the rate of reaction we have looked at in detail again throughout multiple courses in chemistry. There is one of these we haven't seen before, which is pressure. But having just completed the equilibrium topic, I'm hoping that we'll have a better understanding of how pressure affects things. So we've got temperature, concentration, particle size, pressure, and the use of a catalyst. So temperature first of all, this should be very, very familiar. If the temperature is increased, the particles are going to have more energy and they're going to move more quickly. And this is what these little lines represent. They represent the molecules bouncing around much faster. Because remember, temperature is a measure of the average kinetic energy of a substance. So the higher the temperature, the more energy the particles will have to move around. So increasing the temperature increases the rate of reaction because the particles can collide more often. They collide more often because they are moving around at a quicker speed. Concentration. If the concentration of a reactant is increased, there's going to be more reactant particles moving together. Obviously, if you increase the concentration of something, you are increasing the number of particles that are in that substance. So there's going to be more collisions because simply there's more molecules, more particles. The higher the concentration, again, the faster the rate of reaction will be because there are more particles, so there's going to be more collisions. Particle size. By decreasing the particle size of a reactant, we're increasing its surface area. So where this particle is only reacting on the outside surface, if we break it up into smaller parts, there is going to be far more surface area for all of these reactant molecules to collide with each other. So the greater the surface area, the faster the rate of reaction. And you increase the surface area by making the particles smaller. So powdered is best, and small lumps are kind of next up. Large lumps are the slowest. So pressure, if the pressure of gaseous reactants is increased, there are more reactant particles for a given volume. So that's what we mean by increasing the pressure. And as you can see in the diagram here, these particles have lots of space to move around, but when we increase the pressure, there isn't much space to move around at all. So what that means is when the particles are moving around, they're going to be in closer contact with each other, so there's going to be a higher probability of them colliding with each other. So the higher the pressure of the reactants, the faster the rate of reaction will be, because there's going to be more collisions due to the particles being closer together. Lastly, we have catalysts. So we know that a catalyst can provide a surface for the reactions to take place on. Now what it does is it holds the molecules at a favourable angle, which means they're going to have a higher chance of successful collisions because they are being held with the correct collision geometry. So that's how a catalyst helps to do that. Again, it's very important for catalysts to have a large surface area so that more of this can take place. This was quite a short lesson on controlling the rate. As I said, most of it was Nat 5 revision, so I'm hoping that everybody understood that and has been able to follow it along successfully. If not, and you feel like this is an area of weakness, then I would encourage you to go back, look at your National 5 notes, try your very best to complete the open-ended question and get all of your knowledge down on paper. But hopefully you know how to calculate the average rate. You now know how to calculate the relative rate for chemical reactions, and you should be able to explain in detail how all of the factors that we've just discussed affect the rate of reaction. I will see you shortly for part 2, which is going to be energy profiles, where we're going to look at how this actually happens in a lot of detail. So I hope you have a good week, and I'll see you soon.